So I've decided to cut ANOVA from the course, and I will, and I believe you guys will cover logistic regression in your regression class. So that is also being cut. So there's trying to minimize, I don't know, redundancy, I guess. So so in the syllabus, we're skipping weeks 3 and 4 as they're written, and then so I'm just jumping ahead to what I had planned for week 5, which is so originally I wrote kernel density estimation and recursive partitioning. Recursive partitioning just being kind of a fancy way of saying like a decision tree. I think we'll start with the decision tree stuff, and then we'll see how much time that takes. I imagine it will take the full class time. Kernel density estimation maybe only doesn't take that long, but so we'll see. If there's time left over, we can talk about kernel density estimation, and if there's not, then we'll just stick with the tree stuff. Okay, so we'll start with we'll talk regression trees or classification trees, or they might call it decision trees. So this book calls it recursive partitioning, because that's what we're doing. This one says, what is it called? TreeBased Methods. It might be referred to as CART by some. So there's, okay, so I'll just list off all sorts of similar names for the same thing. Okay, so we got tree-based methods. Okay, so we got also known as, so we have CART for classification and classification in regression trees. We also have it called RPart. This is recursive partitioning. Those are probably the kind of two biggest things. Maybe we might just call it a decision tree. That's probably the easiest. Okay, the idea is you got a bunch of data, and then you just kind of sort the data based on different criteria, right? So let's say we had to make a prediction on how someone voted in the last presidential election or something like that, right? So we might, we just start asking questions, right? And these are all yes or no questions, and so it might be like, so one question could be, is this person male or is this person female, right? And then, and if that was the only thing, that was the only question, then you would say, then you'd have to make a prediction, and it would be kind of a majority vote for whatever. And so that's probably not the best thing for talking about the presidential election, but I think overall, I don't know. I don't remember all the things, but I think Hillary Clinton won the female demographic, and I don't know which, maybe overall for men, I don't know if Donald Trump won that or not, if we're just going off of something like that. And then so you would just have basically everybody who falls in one box gets the same classification, or if we're talking numeric variables, that gets the same predicted value, okay? Probably you would split it more than just on one variable, and then you'd say, okay, so maybe the first split will be on, something, race, or gender, or income, or education level, whatever it might be. You just keep, you form a split, and then you keep splitting the data until you get these very specific, maybe possibly 2 specific data, all right, or buckets, right? And you might say like, okay, if the person is a female between age 25 and 35 and is college educated and African American and lives in Southern California, we're going to predict this person voted Hillary Clinton or something like that, right? And then you might say, okay, this person is male, between 65 plus, lives in Alabama, and I don't know, something like this. And then we say, okay, based on these demographic characteristics, after this giant split, we're going to predict this person voted for Donald Trump or something, right? And it might not be 100% accurate. You know, there could be a person that fits all of these things, and that person says, "Excuse me, I did not vote that way," and that would be a misclassification in that case. But the idea is, you know, we're trying to parse things out in such a way. Okay, and so that would be a classification tree if we have a categorical response. Okay, so classification for a categorical response, and you know, regression tree or numeric response. Run out of battery quickly. Okay. Okay. And yeah, the idea is you have your so let's just do a simple example here. Let me just throw this into lecture slides. Okay. So let's start off with a regression tree example. Okay, so we'll have this. Generally, you have lots of variables here, okay? But just to kind of illustrate how the regression tree would work, let's say our x, we've got 1, 2, let me put this in a column actually. So x, we've got 1, 2, 3, 4, 5. And y, let's say, is done some calculations ahead of time. So let me just write these down. Okay, we'll do 1, 1, 3, 7, and 8. Okay, and actually, for the sake of this, I'll plot this in R, and then we'll have a real plot that we can actually draw on. So x is going to be 1 through 5, and y will be 1, 1, 3, 7, 8. Okay, and then I'll just do a plot of x and y. Let's go from 0.5 to 5.5. And y, let's go from 0 to 9. Okay, so we've got this, and let me just... Okay, so here is the plot of data that I'll use. Okay, and so if we have no split, then our prediction for everything, okay, so if we have no split, you know, our quote prediction is y bar. So we do 1 plus 3 plus 7 plus 8. And what is this? 20 divided by 5. So we get 4, and then so our regression estimate looks something like this here. Let's use a different color. Okay, this is what we have. And then we have residuals for each of these. Okay. So we have a residual there, 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 and there. Okay. And then so the RSS is going to be the sum of each value minus our predicted value. This would be kind of 1 minus 4 squared plus 1 minus 4 squared plus 3 minus 4 squared plus 7 minus 4 squared and 8 minus 4 squared. Okay, and so here we would get, what is this? 9 plus 9 plus 1 plus 9 plus 16. And we add that up, and we get a total residual sum of squared of 44. This is where we are right now. This is no split on the data. Okay. With regression trees, we will consider every possible partition on the data. Okay, so here I've got 5 data points, so we have a total of 5 possible partitions. Okay, I could partition. We'll consider every single one, right? So right now, there's already one partition, which is classify everything in the same group, right? And so this could count as like, I just have a partition right here. That's one possible partition, okay? And this is equal to having the partition on this side, okay? Because it just throws everybody into the same group, right? So that barely counts as a partition, okay? But we could partition the data right here, or right here, or right here, or right here, right? So we can basically just draw a split at any one of those points, okay? So a regression or a decision tree would consider all possible partitions, all right? And the decision-making criteria is we want to minimize the residual sum of squares. And a decision tree, the algorithm is greedy, meaning that it doesn't try to look ahead. It just says immediately, I want the biggest payoff right now at this moment. So whatever split I make now, I just want the biggest payoff at this moment, okay? So it's a greedy split, okay? So we go for the immediate quote best payoff. So some algorithms, they have a kind of a look ahead mechanism. It's a little bit more complicated, but they try to look, like another step ahead and say like, well, maybe if I take a less optimal split here, I can make a better split later. We don't bother with that. We're just going to go for the immediate best payoff, okay? And so the immediate best payoff will be a reduction in RSS. Okay, so we'll just try a couple splits, okay, or a few splits, and then I think we'll get the idea. So let's put this right here. All right, so let's say I do the split at x equals 1.5. Okay, So I'm going to split the data right here. All right, so then my fitted line at this point, so for x less than 1.5, we have the point 1 and 1. Okay, we have that coordinate, and so our y bar is just 1, and so y hat is also going to be 1. All right, so we just predict if your value is less than 1.5, we're going to predict this right here. Okay, and then for x greater than 1.5, okay, the y values that we have are 1, 3, 7, and 8, and the mean of those values is, if I add those up, I get 19. 19 over 4 gives me 4.75. This is my y hat and y bar equivalent here. Okay, so I'm going to put in, so 4.75 will be somewhere like right here. Okay, so this would be 5. 4.75 will be somewhere around there. So right here, this is what I have. Okay, and then we'll calculate the residuals for each of these things. Okay, so we've got so we have no residual here, and then we've got these residuals. Okay, and so the RSS here is going to be, so over here I've got 1 minus 1 squared, so that's the 0. And then I've got 1 minus 4.75 squared, and 3 minus 4.75 squared, and 7 minus 4.75, and 8 minus 4.75, yeah? Okay, and then if we add all of this up, we would get 32.75. Okay, so that's the split at 1.5. I'm just gonna how do I shrink this? Okay, and if we did a split at, so I'll just illustrate very quickly here. So if I do a split at 2.5, which is, you know, something like this, okay, this will probably give me, you know, slightly better performance in that my prediction here goes like this, and then the prediction for these values over here is 5.5. Okay, 5.5 is the wait, no, 378. Oh, I'm sorry, 6. Okay, is that work? Okay, so this has a, you know, so this is 3 plus 7 plus 8 over 3. So we have a prediction of 6, and then and I did the calculations here, and then okay, so over here we have basically 0 squared plus 0 squared, the RSS, and then here I've got plus 3 squared plus 1 squared plus 2 squared. Okay, so I get 9 plus 1 plus 4. I have a RSS of 14. Okay, and then we'll just for, okay, and then lastly, if I do the split at 3.5, okay, so it considers every single possible partition. So here I'll do this split here. Okay, and so we would have a split at 7.5, and then I think over here we would have a split at 1.67, so 1 2/3 right here. Okay. So I should draw the residuals. So this is 1.667, and over here I have 7.5 as my predictors. So the RSS of these points is going to be 0.667 squared plus 0.667 squared plus 0.333 squared plus 0.5 squared plus 0.5 squared, and when I sum all of that up, I get an RSS of 3.1667. Okay, and so we can imagine this process being carried out, you know, across all possible partitions. So I mean, there's really only one more partition to consider in this example, and we would take the one that minimizes the RSS, and we say, well, this is the best split. Okay, and so if our tree ended here, we would just say, okay, is x greater than 3.5? If it is, my prediction for y is 7.5, and if x is less than 3.5, my prediction for y is 1.667. Okay, so this so after one split, our tree looks like this. Okay, is x greater than 3.5? Okay, and if the answer is no, then y, our predicted y hat is 1.667, and if the answer is yes, our predicted y hat is 7.5. Yes, question?
Will it consider like sort of piecewise partitions? So like, you know, if you are greater than 2 and less than 4?
No, it only does a binary split. Okay, so it just and it only looks at one variable at a time. So here we only had one predictor variable for the response y, but you could imagine we could have two predictor variables. Okay, so I'll illustrate that. So if we had two predictor variables, and so we've got kind of this plane here, right? So we have x1 and x2, and then this is our response y, and we've got some kind of surface, then it's going to only consider splits on one variable at a time. So all the splits are perpendicular to the axes. Okay, so so this just yeah, so we just get so this will be x1 and x2, and so you'll only get you'll get a split that looks like this. This might be kind of the first split. Okay, so it would consider all possible partitions on x2, all possible partitions on x1, and it picks the one that maximizes the RSS change, okay, or minimizes the resulting RSS. Okay, so you know, consider all possible splits on x1 and x2, one at a time, and then do a split. Okay, and then after you've done this, just you pick one of the sides. Okay, pick a side, probably the one with a greater RSS after the split. Okay, usually, but it doesn't really matter. Okay, usually the side with more more RSS, and then say, okay, what's the next split I can do that will minimize the RSS for one of these sides? And so you might look at this side, and it might be like, oh, okay, we can draw a split right here, okay, after considering everything. That's just one possibility, okay? And then, and then you might say, okay, well, we've done a good job of minimizing whatever. With x2, you're still looking at all possible splits over x1 and x2, and it might be that x2 is still the best place, and so you might do a split right there, and then after that you might draw a split right there or something, okay? And you get partitions that kind of look like this. You don't get you're not going to get any funny shapes in here. It's going to just be like, we've given you a knife and you have to draw a straight line, and starting at one of these things you've got to draw a straight line, okay? And so if I had a number line, you know, if this is like 0, 1, 2, 3, 4, 5, 6, 7, and this is, I don't know, 1, 2, 3, 4, 5. Okay, so then the tree that corresponds to this, how do I don't know how to shrink. It says use 2 fingers. Oh, there we go. Okay, it's a lot trickier. All right, we're gonna have to live with that. Okay, so the tree here would probably, at least in the way I drew it, would be, is x2 greater than 2? Okay, and we would say over here, if the answer is no, then we would do the split of, is x1 greater than 3? And then if it's no, then we'll call this region 1. And if it's yes, we'll be in region 2. Okay, over here, we have, if x is greater than 2, then the next split is x2 greater than 4, okay? And if the answer is no, then that puts us in, we'll call this region 3. And if the answer is yes, then we have another split to consider, and that goes in, whoops, then we have, is x1 greater than 6, okay? And if the answer is no, we're in region 4. And if the answer is yes, we're in region 5. Okay, and again, we look at all the data points, and at every spot we would consider all of the possible splits that we can make for one of the variables. Obviously, without the computer, this is not really possible, right? Like, to do something by hand, it would be ridiculous. Only in the toy example with 5 data points can we kind of do that. But but with the computer, it's easy, right? You just you kind of sort your data, and you just say like, all right, consider drawing a split here, 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 and then take the whichever region it is, the prediction. So here, our model is only capable of producing 5 predicted values. It's not a linear model. Like a linear model, you plug in an x and you get a y, and it's however big or small your x is, you're going to get a different value of y, right? You get infinitely many possible predictions of y. Here we just have 5 possible predictions for what y is. Y is, whatever the mean of the data points in this place is, that's what we predict. Okay, and if it's a classification system, it's something similar, except we just take a majority vote there. I'll talk about that in a moment. But is this okay? The idea of creating a tree using the RSS residual sum of squares as our deciding factor onto where to put a partition. Okay, and so when we make a regression tree, we keep making splits until we reach some kind of stopping criterion. Okay, so we just keep partitioning the data, and then after partitioning the data, we look at the resulting spots and we partition that, and we look at the resulting split and we partition that, and we keep going until we reach some kind of stopping criterion. The stopping criterion could be like the minimum size of a resulting partition has to be at least 5 or something, right? You might have a minimum number of observations. That's a common one. Or you can say, you know what, don't grow the tree more than 10 splits deep or something like that. Okay, so you have some kind of stopping criterion. It's often a little bit arbitrary in terms of where to draw your how far to keep going. Okay, so keep splitting. Okay, till you reach criterion. Okay, and these are examples: maximum tree depth, or minimum partition size. Okay, and so you reach that, and then you stop. And then, once you are done with that, the next step, so often, if you have if you say keep splitting the thing until you're, let's say you have not a good stopping criterion, minimum partition size is going to be 1, okay? Then you're going to have a series of questions that will fully define every single data point in your data set, right? And that's definitely overfitting your data, right? So in order to avoid the overfitting of your data, then you can prune back the tree, okay? And pruning back the tree, often we do it via cross-validation, or we have some kind of method for to decide how to cut back to make our tree less complicated. Okay, so then okay, so we can, so this can build very complex trees that may overfit the data. Okay. So we might implement a way to prune back the tree. So we're using these kind of gardener analogies here. And oops. Okay, and so the we'll say let T0 be the very complex tree. Okay, so this could be I can't even fit everything on here, but something like this. All right, so if this is T0, then we may choose a subset of this tree. Okay? So some tree T is a subset of the tree. Okay, and this subset tree T may be maybe this part of the tree, just this part or something like that. Okay, so this is some subset of the tree, and this might be just what's worth keeping, and all of this other stuff, maybe that's not worth keeping or something like that. Okay, and so how do we do this? Okay, well, we can do something called weakest link pruning or cost complexity pruning. Okay. And what we have is we're going to try to minimize not the RSS. The RSS is this, each value minus its prediction, right? So we're going to minimize this, except we add on. So we're trying to minimize RSS, the residual sum of squares. However, we include basically a complexity penalty, like a complexity tax. Okay, and this is called it's going to be alpha over t. Okay, this is how many terminal nodes do you have? Like how many resulting buckets do you end up having? Okay, and so this is a number of terminal nodes, and this is kind of like a tuning parameter, right? Okay, so we're still minimizing RSS, but it's not just RSS as the sole deciding factor. Okay, it's RSS plus a kind of a penalty for having a tree that is unnecessarily complex. So we can say, you know, if this number is really big, it's going to every time you add a terminal node, it's going to add a lot, right? And so therefore, the drop in RSS has to be fairly significant to outweigh the cost of adding an additional terminal node. Okay. On the other hand, if this is, well, if you put this at 0, then there's no penalty for adding terminal nodes, and you just end up getting the super complex tree that only stopped because of your stopping criterion. Okay. But yeah, so you'd pick some kind of number here, and based on the number you pick, this will say, okay, well, each terminal node I'm adding, you know, my reduction in residual sum of squares has to outweigh that, basically. Okay, and you would have to search. The computer would have to search across all possible subtrees. Okay, of which, you know, there's going to be a lot, but the computer can do it. You know, it searches all possible subtrees, and it figures out kind of the this total, I guess, metric here, which is a combination of the RSS plus, you know, basically complexity parameter. Okay, and so, you know, to do this manually would be very tedious, but with a computer, it's not too bad. Yes.
is the alpha just random?
It's not. We would actually use cross-validation to kind of pick the alpha that we would want to use. Okay, so we would often kind of. So last week, cross-validation, we said you split the data into like maybe 10 chunks or something, right? And each time you would use 9 out of those 10 chunks. Okay, so using 9 out of the 10 chunks, you design it, you fit a huge tree, and then you calculate kind of which subtree is best based on big values versus small values of alpha. So you kind of have a function of which tree to select based on the alpha. Okay, and then you do this for all of the different folds of the data, and then there would generally be some kind of, we're hoping, some kind of consensus of the different folds that says, this is the alpha that will kind of give us a good subtree to use. Okay, and so we would, so we would pick a different alpha. It's not arbitrary. The alpha is selected, via kind of KFold cross-validation. Okay,
Why
so
didn't it just end up converging to 0 every time?
so after you pick the alpha, the way the KFold cross-validation works is so let's say you have okay, so here, let me kind of illustrate how the KFold cross-validation works in picking alpha. Okay, so let's say you have alpha equal to 0, right? Okay, and then we're using we'll have 9/10 for our quote training data, and then we have the last 1/10 for our test data. Yeah. Okay, and then so with our training data, if alpha is equal to 0, then we will end up picking the best tree is going to be T0. This is the one that T0 minimizes basically the RSS plus penalty for the training data, right? Does that make sense there? Okay. So now we have this, super complex tree. Okay. And then now we plug the test data into here. Okay. What if this is overfitting the data? Then we're going to get poor performance of the tree on the test data, because this might say like if the person is this and this and this and this, and also wore a red shirt and writes with their left hand and drives a Toyota, then we're going to predict this, right? And so now if we happen to find something similar to that, then this is no longer a good predictor here, right? So we plug this into here, and if the model overfits the data, overfits the training data, we will get high test RSS. Okay, and so with kind of alpha equal to something other than 0, another value. Okay, maybe we find this tree minimizes the RSS plus penalty, and then after fitting the test data, you know, our test RSS is also small. So we would pick the alpha that basically minimizes the test RSS when across the different folds. Okay, so you know, you plug in the test data onto your tree, and if the tree is overly complex, this is going to be this will be end up being high. Okay, but by pruning it back, you would you can find the alpha that's going to provide the tree that minimizes the cross-validation, you know, kind of your test area there. Okay, and that's the alpha you would use, and then you'd kind of get your tree that way. Okay. Okay, so that is building a single tree and pruning it back. Okay, for a regression setting. I guess pruning it back is still the same for a classification setting. Okay, are there any questions? Okay, let me just talk about the classification. Okay, so a classification tree. Basically, you do the same thing. You're picking, you consider all possible splits. Okay, so we consider all possible splits, except our deciding criteria is not going to be residual sum of squares. Okay, so we have there's kind of a few different metrics, different ways to record performance. All right. Okay, so basically the prediction for a terminal node is a majority vote for that node. Okay, so if the terminal node has 7 class A and 2 class B, then we predict A for this node. Okay, and that's basically it. So we have a few metrics. Okay, one is just prediction error rate. Okay, and this is basically just number of misclassified or misclassified predictions over total number of data points. But it turns out this is not really the best. Okay, this is doesn't actually, the performance of using this metric is not very good. Okay, and so there's two other metrics, and they give almost the same performance. Somebody did a study. Is there a difference? Is there a real difference between these? And they found that, you know, only in like 2% of scenarios is there a slight difference, and even that difference is not a big deal. Okay, but one is called the Gini index, and this is basically summed across all regions. And p hat being kind of the purity, the majority in that terminal node. So p hat is kind of the proportion of the majority. Okay, so if the node is 7a and 2b, then p hat would be 7 out of 9. Okay, and so if you have nodes, terminal nodes that are completely pure, then you'll have p hat equal to 1 or 0, and that will give, and you're trying to minimize the Gini index, right? And this will be maximized when p hat is 0.5, and that means that's indicative of this is not a good terminal node, right? If your terminal node is half A and half B, you can't make any good predictions, right? That's just, you're at a coin flip. Okay, so this is the Gini index, okay, proportion of the majority, all right, and we want to minimize this. Okay, and then the other is entropy. Entropy is p hat times log, or I'll just write log of p hat. Okay, and so if you have a pure node where p hat is 1, I'm sorry, this is if you have a p hat of 1, then you get 0, and then if you have anything less than that, you're going to get a negative number there. Okay, and so we sum that up, and we take the negative it, hoping to minimize this. Okay, and so both of these will favor nodes that have high purity. Terminal nodes of high purity. Okay, and that's how we make decisions. Same idea as before. We consider every possible partition, and we just have a greedy criterion. So if we're doing Gini index, then we find the split that is going to minimize the Gini index after making the split. And that's it. Okay. Yes. Majority vote. So if your terminal node has 7 that are in class A and 2 that are in class B, then our prediction for all points in that terminal node will be class A. Okay, and so we would correctly predict, or I guess the training error is would be 2 for that terminal node, because all of these people would be predicted as class A or something like that, right? And so right, so this would be based on maybe we do these demographic splits, right? And we say, okay, if you're this kind of fit this category and this category and this category, we predict this is your behavior, that you voted this way or you voted the other way, right? And so perhaps I don't know, a certain candidate wins 80% of a certain segment, right? Like people over a certain age and of a certain race and a certain education level or something like that. Okay, so in that case, we would just say everybody in that category fits will be predicted as having voted this way. But then and the p hat would be 80%, but that means 20% in that category were predicted incorrectly. So you would have a Gini index of 0.8 times 0.2. The log entropy would be the entropy would be something else, something like that. Okay. Does that make sense for the classification tree. So it's so for the regression tree, we just predict a value based on the mean of the data points in that segment, and for the classification tree, the prediction is just whichever category or whichever class has is the most represented in that segment partition. Yes.
So if you had a tree and you had like an idea that like one of the parts of the tree was working really well, but the other part was causing all of your error, could you do this like the Gini index? Could you do it on like the subtrees of each of those parts to see how each parts of the tree are performing?
That's related to boosting. Yeah. So we'll talk about some of these ideas here. But generally, even without doing something like that, once you have a node that is pure or very pure, the kind of when you're searching for what's the next split to make, you're not going to touch the ones that are working very well, right? Because you're kind of searching for across all possible splits to make, and if these ones are working very well, you don't have to further split your data, right? And it's just when you get down to here, where do I need to split my data? And then you're starting to balance between additional splits and whether or not. How do I go back? Okay. I don't know. You're balancing. So before we had the RSS plus the alpha times the tree complexity. Now it would be one of these plus the alpha times the tree complexity. Basically, the cost of making your tree more complex cannot outweigh can't outweigh the gain that you're getting from the Gini or the entropy change. Okay, so that's that. So the trees, they're very simple, and the single decision tree all by itself is not widely used because its prediction power, even after pruning, is just not that great. Okay, the single decision tree alone does not have good predictive power. Which isn't, it's a little unfortunate, okay? But that's because, if you think about it, how the tree splits, let's say you end up with 10 terminal nodes. With a regression tree, that's just 10 different values that you can predict, right? So yeah, the predictive power is not going to be that great, okay? So the single decision tree alone doesn't have very good predictive power. So people have come up with ways of trying to improve the use using a tree. Okay. The nice thing, though, single decision tree does not have good predictive power. However, a major pro is that it is very easy to explain. Okay, like people are used to the idea of kind of segmenting the population based on certain characteristics, right? So it's very easy for someone to understand what when talking politics and stuff, it's very easy for someone to say, okay, for people of this race and this gender and this age group and education level, this is how we would predict them to behave, right? And that's very easy for people to understand. And even if it's like 75% follow this thing, which means, you know, a whole 1/4 of that group is predicted incorrectly, which is not a great error rate. People understand that kind of, I guess, explanation of the thing. Okay. So that's a nice thing of having a single decision tree. Okay. But yeah, you might have, you can at best hope for, like, yeah, error rates that aren't too crazy big, right? Okay, we have methods, and we'll start with kind of the I guess the simplest, and then we'll talk about how these get better to improve our decision trees. Okay, so the first method for how do we improve decision tree performance, okay? Okay, so the first one is basically bootstrap, but we call it bagging. And this is bootstrap applied to trees. So what the tree does is it takes your data and it tries to partition it up and minimize either your RSS or your Gini index or something like that. Okay, so what does bagging do? Well, we take our original data and we bootstrap it. So bootstrap is basically saying my original data is representative of the population, so I can make infinite copies of it, and then I'm going to draw a sample from that pseudo population. Okay, so we bootstrap this. Okay, and then so we might end up getting maybe we'll have 100 different samples that are kind of similar, different different samples that are at least based on the original data. Okay, so we have maybe this is bagging 100 trees, but you could do even more. Okay, then for each one, you would build a decision tree. So now build a decision tree for each one of these different samples. So now you have 100 different decision trees. Okay, and you don't even bother with the pruning. Okay, just let the trees be complex. We don't care. Okay, let them be complex. Don't bother with pruning. Okay, so now we have 100 trees. 100 trees. All right, and so these trees, they're all going to be kind of similar. They're all similar, but they're not the same, right? Because each of these bootstrap samples of data do differ from each other a little bit. So one may have made the first deciding criteria to say, like, I'm going to do the split at x equals 1.5, and then someone else, another tree might say, I'm going to do the split where x is 3.5 or something like that, because the resulting data may have looked different for these different data sets, right? So you've got different kind of different splits, but they're kind of similar. Okay, so how do we make a prediction? Okay, so for a prediction, okay, we run our test data through all 100 trees. Okay, for prediction, so we'll do one test case. Okay, run the test case through all 100 trees. Okay, and based on and so you're going to get 100 different predictions. Okay, some of them might be very similar, but they're not all going to be the same, right? So you'll have through all 100 trees. Now you have 100. You now have 100. I don't know why I'm drawing in a circle here, but okay. So we now have 100 predictions. Okay, and what do? Our final prediction is just the average of all 100 predictions. And that's bagging. So we kind of shake up the data a little bit. All right, so we get like 100 copies that are similar, but they're all a little bit different, and thus the resulting tree will all end up just a little bit different from each other. And then with our test case, we feed them through all of them, and we get 100 different predictions, and then we just average those together. Okay. So this improves kind of our performance, but the drawback is it's hard to explain each thing now. Okay, because whereas before we just had kind of one criterion that says, was the person over age 30 or under age 30? And based on that, we can make a prediction. But now, one tree used the criteria, is the person over age 30 or under 30? Another tree used the criteria, is the person over age 35 or under 35? And another tree said, is it the person age over 18 or under 18? Okay? And based on all of those things, this one was, if somebody comes in at age 33 or something, they're over the deciding criteria for two of the trees, but under the deciding criteria for another tree. And so we're getting different values, and we just average, those different values together to kind of get some kind of conglomerated prediction. But it's not that easy to predict. Yeah, go ahead.
So since we're not pruning any of the trees at any point, is there a possibility for overfitting the model? Oh
yeah. So each individual tree almost certainly has overfitted the model, but you're hoping that one of them overfit in this way, but the other tree did overfit in a different way. And that overall, because you're just kind of averaging everything across the board, the possible overfits get kind of blend out when you average them or take the mean. Yeah, John.
If you're building a tree with multiple features to get into account, and you're running iterations, like, is it possible that, so for example, you're running a categorical or the classification tree, where it'll pick optimize to the mean.
Yeah.
What if that subsample optimizes to like they start at different variables for each like of the first node? So like, is it possible for like one tree to start at age and another one start at state? Like,
yes, absolutely. Yeah.
So how would you reconcile the average there?
You just take the final result. So we don't care what path it took to get to the bottom node, right? So tree 1 can say like, okay, we looked at the state, then we looked at race, and then we looked at gender, and then we looked at age, okay? And then tree 2 says, you know, I didn't even look at state. We looked at age, and then we looked at income, and we looked at, you know, this and that. And so tree 2 maybe has a totally different set of predictors or something in a different set of order, in a different order, because things are different, okay? But when you do your test case, you say, okay, I fed test case into tree 1, and we followed this path, and it said we're predicting this, okay? And then we put in the same test case into tree 2. It had totally different questions and a different path, and it said the prediction here is something else, okay? And maybe the predictions might be totally different for the different trees, but you're just averaging them and saying like, well, I'm hoping that when I average all of these different trees, that we get something kind of around what's correct. And it turns out that even though you average a bunch of different things, it turns out to be, you know, more correct than a single tree. Okay, but yes, yeah. How do you explain that though? You lose the ability to explain what's happening, how you came up with this prediction. You lose that ability, right? Before with the single tree, it was easy. You said, well, we split the population based on, you know, the states, right? And we say, okay, well, if they lived in California, we're going to predict this, and if they lived in Texas, we're going to predict this, right? And then you said, well, and then further that, you know, of the Californians, we said, you know, which county did they live in, right? And if they lived in LA County, we predict this or something like that. Yeah, and we can do that. But yeah, with different trees, you'll say, you know, one may be like the one that used the state information, and another tree used something different and unrelated. But you're hoping that at the end, when you average them, you get something better. Yeah. Okay.
What exactly do you average?
So if you have a classification tree, then it's just the majority vote, right? So if you have 10 different trees, 7 of them said, based on the test case information, 7 of them said class A and 3 of them said class B, then your quote average classification is going to be class A. You just say 7 versus 3, the side with 7 wins. Yeah. And then if you end up something where it's like totally split 50-50, you don't have a very good model for that test thing, and then you're just at a point of, you know, my model didn't help me, I might as well just flip a coin. But yeah, so you either average the numeric output with for regression, or you just take a majority vote of how the different trees set, right? So that's how this works. Okay. Is that okay for bagging? Okay, so we're just using the bootstrap. We kind of perturb the data so that so we get slightly different trees. Okay. So that's bagging. Then we have random forest. Okay. Random forest is basically bagging, but I guess it's fancier bagging, okay? So it's like a fancier version of bagging, okay. All right, so how does random forest work? Same idea first. We kind of bootstrap our data. Okay, So now, sorry, I'll do a bullet point. Okay, we bootstrap our data. So let's say we get 100 different bootstrap samples. Okay. What we do now is we purposely handicap our tree making ability. Okay, we say don't look across all possible splits, across all possible variables. You are now only limited to this small random subset of variables. Okay, so maybe you have 40 different variables you can look at, right? We might say you're only allowed to look at 5 of these. Okay, so so for each sample, bootstrap sample, we allow the tree to consider for each bootstrap sample, and I guess for at each node, at each decision-making node. How is this? How do we not? Okay. Okay, there we go. Each decision node, we allow the tree to only consider a subset of the possible variables. So what's the letter here that we use? P out of the M out of the P possible variables. Okay, so tree can only use M out of the P variables. Okay, and then basically, so we end up with 100 different, probably very different looking trees. Right, so we end up with maybe 100 very different looking trees. Okay, and then we make predictions the same way as before. We put our test case in, we get 100 different predictions, and we average all of those predictions. Okay, so how is this different from bagging, and why is this better than bagging? Okay, well, so earlier we were just talking about this scenario where, you know, one tree split based on state, and another tree split on age, and another tree split on race, or something like that. Okay, a lot of times when you do bagging, it's very rare that that kind of variation in trees appear. Okay, sometimes in your data, one of the variables is like the strongest predictor. Okay, and so when you're doing your initial split on RSS, even though you've mixed up the data, even though you subset, bootstrap the data and gotten a different sample each time, maybe that one predictor is so strong that every single one of your trees ends up having that same predictor at the top, right? So if we're talking, I don't know, whatever we're talking about, maybe, which state you lived in or which county you lived in is the strongest predictor that we have. And so, so no matter how we cut the data and shuffle it up, we're getting trees that look almost identical, at least for maybe like the first 2 or 3 levels, right? And it's only after we get into the 4th or 5th level where we're starting to overfit the data, do we start getting differences. Okay, so if certain predictors are like super strong, you might end up getting 100 trees that look almost the same except for the parts where it's overfitting. Okay, and then so then when you average these things, you're averaging basically 100 results that are practically the same and not really giving you much information, right? So by forcing some of the trees to use a predictor that's different, okay, by saying, you are not allowed to look at the location. Now you have to use this other data. Now you have to use this other these other factors to make your decision. By forcing the trees to be different in that way, when we take the average of them, we end up getting better predictions. Okay, and so that's kind of the idea of when you have, if you're looking at the average of highly correlated data, you have high variance in your predictions. But then if you decorrelate your data, if your data has low correlation across the different things, then the average of those will have a much lower variance. Okay, and that improves the performance of our tree, of our predictive model. And so we call this a random forest because it's made of, I guess, a bunch of different trees or something. Okay, so so this prevents almost all of our trees looking to be nearly identical at the top levels. If our data has certain variables that are strong predictors. Let's take a pause here, and then we'll come back and we'll do some demos in R, and then we'll try talking about boosting as well.